Okay, we're going to talk about spanning sets. Now we've just been talking about linear combinations, and we're going to use that concept to define a good way of specifying sets of vectors. Just for a warm-up, you know that a line is any multiple of a single vector. So if I have a single vector and I take every possible multiple of that single vector, it's going to be a line. Okay, so this is a linear set that's actually can be considered as a linear combination of one vector. Now if you take two vectors and consider all linear combinations of two vectors, well, if you think about it, you can actually reach any point in this plane. For instance, this point here would be a multiple of this vector, something like this, plus a multiple of this vector, something like this. Okay, so I can think of the points in the plane as a linear all points in the plane can be obtained as a particular linear combination of these two vectors. So this shows you how linear combinations can generate sets. All right, so let's go on. Okay, so here's the definition of the span of a set of column vectors. So given a set of column vectors, u1 up to up, the span, written with these angle brackets, you see, is the set of all possible linear combinations of the p vectors. And here's how it's defined. This angle brackets s, span of s, is equal to alpha 1 u1 plus alpha 2 u2 plus dot 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 plus alpha p up, where the alphas are constants. Again, here he says complex constants, but typically we consider real constants. And so each vector has a constant, and you add them all together, and you can write it this way using summation notation. Okay, so every different alpha is going to generate a different vector. So the set of all possible linear combinations gives me a set of vectors. One important point is that usually this set S is finite. In this case, this S has p vectors. However, the span of S has an infinite number of vectors. Same way, if you take a single vector, its span is an infinite number of vectors, any multiple of that single vector. Okay. So here's an example of a span. I have 5 vectors here. I could take this linear combination. Let's see what's going on here. 2 times the first vector plus 1 times the second vector plus minus 1 times the third vector plus 2 times the fourth vector plus 3 times the fifth vector. And that will give me a vector in the span. Okay. Here's another possible vector in the span. 5 times the first vector minus 6 times the second vector, etc., etc., etc. Add them all together. You know that you add them component by component. And you'd get this vector also in the span. So there are lots and lots of vectors in the span. Okay, here's another vector in the span. Here's another vector in the span. Okay. All right, now, suppose we ask the question, is this vector in the span of these 5 vectors? That's a general question we can ask. What that means is that we're asking whether this vector u here can possibly be written as a linear combination of the 5 vectors. So we'd need to find constants that give us the proper linear combination. Okay? Now actually this is a solution to a linear equation. You want alpha 1 times 1 plus alpha 2 times 2 plus alpha 3 times 7 plus alpha 4 times 1 plus alpha 5 times minus 1 equals minus 15, etc., etc. The first, second, third, fourth entries of these vectors give 4 equations involving alpha 1, alpha 2, alpha 3, alpha 4, and alpha 5. And they're linear equations. So we can actually express this system of equations using an augmented matrix. And you can recognize this matrix of coefficients consists of the column vectors that form the linear combination. Okay, so we're looking at linear equations in a new way. A system of linear equations can be thought of as linear combination of column vectors is equal to the constant vector. So same old linear equations thought of in a new way. Once we have it in augmented matrix form, we can use our same techniques that we've used before. You can take this augmented matrix, row reduce, and read the answer off of this row reduced matrix, as we've done several times before. So the question is, the original question was, is it possible to express this vector here, minus 15, minus 6, etc., as a linear combination of these vectors here? Now, if it's possible if and only if we can find a solution. And this form of the reduced matrix guarantees that we can find a solution. Let's give an example. To find a solution, you'd set values for the two free variables. In this case, the free variables are x3 and x5, or we're calling them alpha 3 and alpha 5. And from that, we can derive values for the other variables. For example, if I set alpha 3 is equal to minus 2, and alpha 5 is equal to 2, if I just chose those values, then from this equation here, from this last equation gives me what? It gives me x4 is equal to minus 7 plus 2x5. Remember, you take this one here, when you move it to the other side, it becomes a plus. Right? So if we take this value, and remember, x5 or alpha 5, I should say alpha 4 rather. So let me correct that. I should say alpha 4 is equal to minus 7 plus 2 alpha 5. All right, so let's see if that works. If I choose alpha 5 is equal to 2, I can plug that in here, so that gives me 4. Minus 7 gives me minus 3, which agrees with this one. And you could get all these other solutions here using the same method. Okay. All right, so this particular solution means that I can write this u vector as a linear combination of the column vectors. Okay. Let's try again. Let's try this other vector here. Is this vector also in the span of these column vectors? All right. Well, it's the same question again. We still have the same column vectors, which gives us the same coefficient matrix. The only thing that changes is the constant vector at the end of the augmented matrix. When you row reduce, you end up with this, which you can see right away because there's a pivot entry in the last column. You can see right away that this is inconsistent. So there's no solution. This is not in the span. Okay, it's not in the span. All right. All right, so consider this spin. All right, so that's end of story. So let's consider another example. We have three vectors here. Consider the spin of these three vectors. Well, here's one vector in the span. I could take 5 times the first minus 3 times the second plus 7 times the third. We have a linear combination. And we could choose any combination of values. This was our one choice of alpha 1, one choice of alpha 2, one choice of alpha 3. We could choose any alpha 1, alpha 2, alpha 3. Okay. So you can ask whether this vector is in the span, and you use the very same method. Here you have vectors here. These vectors can be considered as columns of a coefficient matrix, and we use this vector here as the constant vector in the augmented matrix. You can see that also from here. The linear combination creates this system of equations, and we simply create the augmented matrix from this. We row reduce. If you row reduce from this row reduction, you should be able to get an answer. Notice that alpha 3 is a free variable. So for instance, I have alpha 2 is equal to 2 plus alpha 3, and this we get alpha 1 is equal to 3 minus alpha 3. Okay, so I could plug in any alpha 3 and get alpha 1 and alpha 2. And that gives me a linear combination. And that solution will give me values of alpha 1, alpha 2, and alpha 3 that give me this vector W. The system has infinitely many solutions. All right, so that pretty much talks about what I... Okay, so here it's doing the same thing, so you can see the same example. Okay. All right, now there are several examples here. I invite you to read through these examples. He's emphasizing this point to make sure you understand what's going on. Okay, so that's all I'm going to say about that subsection. Let me go on to the next section here, spanning sets of null spaces. Or rather, let me stop here and I'll